So Brian Blanton is a physical oceanographer at the Renaissance Computing Institute, which we call RENCI for short, at UNC-Chapel Hill, with extensive experience in forecasting and prediction in the coastal ocean. His research focuses on storm surge and tide dynamics, interaction of storm surge and coastal river flooding, and the impacts of climate change and sea level rise on coastal hazards and risks. He has led large projects for FEMA-funded coastal flood insurance studies, where the primary computational tool is the storm surge, tide, and wind wave model ADCIRC/SWAN. His expertise includes forecasting of coastal weather levels and waves, model verification and validation, scientific programming, and high-performance computing. And to round it all off, he says he likes road biking, soft jazz, and walks at Duke Gardens. All so very lovely. Unbeknownst to Brian, I slipped in one more resource for you guys just an hour or so ago into Sakai, and it is a link to a website that's still under development, so don't run around and advertise it, but it shows the ADCIRC prediction system with lots of pretty colors and everything. And I decided that you guys deserve that after looking at Brian's readings, which were very, very appropriate, very nice, but they have some of those scary math formulas in them. So yeah, pictures are good. Okay, so Brian, I'm gonna ask you to start your presentation. We'll go for around 30-ish minutes or so. Put your questions during his presentation during the chat, in the chat, and I'll try to monitor that. So take it away.
All right, great. Thank you, Anna. Hopefully everyone can hear me well enough. I'm going to blaze through this talk that I've given a number of times in various settings, one of which was actually this class last year, right before COVID hit. So as Anna said, my name is Brian Blanton. I'm a research oceanographer at UNC and a funded principal investigator with the DHS Coastal Resilience Center that I'm sure you all have heard of. Just as a point of getting through this, I can't see any faces at the moment, which is fine with me. My little window that has all the gallery people in it is gone. I don't know where it went. So I'm assuming that that's okay and that everybody's awake. It is 4 o'clock. So anyway, let's go through this pretty quickly. Hurricane-driven storm surge for coastal hazard and risk assessment. By and large, we're going to talk about, if I can find the mouse. Sorry, it's not like I haven't done this 100 times in the last month. Storm surge, data and observations models, hurricanes, and the risk of living at the coast. And this is in, it's in approximately this order, but we'll see. I mean, there'll be some slides that I'll probably decide to skip as we go along out of time. I'll really do my best to keep this in under 35 minutes or so. So this picture, there's a bunch of pictures on here. I mean, a hurricane, a little girl standing or sitting at the beach, not looking at the waves, but paying attention to other things. The port of Savannah, Georgia, which has, fairly large responses to coastal hazards. In particular, hurricanes would be a pretty bad thing here. Turns out it's very statistically unlikely for a hurricane to hit the coast of Georgia, compared to South Carolina or even North Carolina. And there are sort of reasons for that we can get into. The picture in the lower right is water overtopping a levee during Hurricane Katrina in New Orleans, and this is along the I-10 corridor somewhere. Just to say that we depend on the coast. I mean, most goods and services that the U.S. population consumes one way or the other comes through a ship. And those go through ports, and those ports are sensitive to certain environmental and sort of earth science related hazards. And again, hurricanes are kind of one of the big ones. So so why study or compute, for that matter, storm surge? So these kind of statistics are all over the place, and they're not particularly new. But 44% of the world's population lives within basically 100 miles of the coast. And that's partly due to the fact that not only is that where that's where the goods and services are really coming through for the most part. That's, as a consequence, that's where the jobs are. And then as sea level rise, as sea level increases over time, that population is going to get compressed. And not only that, more and more people are moving there. So the consequences of things like storm surge and hurricanes becomes more and more important over time. And in particular, coastal development planning, policymaking. I mean, a lot of those issues are not tied into the science of, climate change, global change, whatever you want to call it. But even more specifically, just, what is it that the floodplain actually looks like statistically, so that people could make some rational decisions about how to build, how to develop, and in particular, where not to build and develop. And so I failed to read the syllabus of this course, although I think I recall that y'all have at least talked a good bit about, FEMA, kind of what it's supposed to do. So I'll skip over a lot of that. But the point here is that they define coastal zones for flooding, and then somebody on behalf of FEMA computes a bunch of statistics, and those statistics go into FEMA's flood insurance rate maps. So the rate map really is one way of attempting to hedge against the potential hazards and consequences of things like hurricanes in the coastal zone. And again, sea level rise, i.e. climate change, impacts on the coastal zone are a really well studied at this point concept, although of course what's the real driver of a lot of the concern is the uncertainty in estimates of how much sea level is going to rise over what time frame, because that's subject to a lot of the things that we're going to talk about. So, just an interesting thing. I mean, the physics of storm surge, we actually understand pretty well. What we don't necessarily understand are the consequences of storm surge in an area like, in this case, Ocean City, Maryland, right before Hurricane Sandy hit, and then right after, right? So in other words, this entire area just gets obliterated. And so one question that people ask is, well, was it anticipated that this would be the case if you had a hurricane like Sandy impact this area? And that actually boils down to, in many cases, how good are the FEMA maps that are used to delineate whether or not one pays flood insurance for something like a home mortgage, or whether some other private insurer actually what they would charge to insure, let's say, a big industrial complex. So in general, the risk equation kind of looks something like this. There's a bunch of varieties of this, but this is kind of the simplest one. So the hazard is really, what's going to happen, and then potentially some probability associated with the event actually occurring. Think about a hurricane, and something along the lines of it's fairly rare, right, compared to other things. And I'll give an example of that in just a minute. And then you multiply that probability somehow by consequences, meaning dollars. Although it may not be dollars. I mean, it could actually be social institutional, capital, or some other quantity that's a little bit harder to link to dollars, but nonetheless is a critical factor in the way that the coastal zone functions and the way that people live in it. But really, it's the product of these two things that's probably more important, because that really tells you what the risk level is. So if you had a very likely high probability event occurring, let's pick a hurricane that hits a part of the coast that's unpopulated. There's really no natural resources there. I can't really conceive of a situation like that. But in other words, pretend the consequences were zero. Then in that case, the risk, or really the policy implications of that hazard in that area are kind of zero in a mathematical sense. I mean, so that's really the distinction between risk and hazard, is that the risk really does attach something about the consequences of a hazard occurring. And so typically they're conditional probabilities. In other words, you can't really talk about the risk without assuming something about the probability of the hazard. And this goes a little bit into things like, what is the 100-year flood? Does it occur once every century, right? The answer, of course, is no. The 100-year flood is technically, it's a misnomer. It's really just it's a consequence of the way that you compute probabilities. But it's the expected water level expected to be equaled or exceeded about once every 100 years. So what that really means is that there is every year there's a 1% chance that that flood level, whatever it may be, is going to be equaled or exceeded. So FEMA conveys these on rate maps by lines. And for instance, the 500-year flood, which is, I think it's on the rate maps, although it's not clear to me why, is the 0.02 annual chance occurrence. So every single year that goes by, there's a 1% chance of having the 100-year flood. So really the risk community tries to get away from phrases like the 100-year flood, because it just doesn't really mean much. And people misinterpret it, meaning that, well, it happened last year, so we have 99 years before we have to worry about it again. So let's just assume that you want to lower risk, and we'll take an example, a personal insurance example. So if you are worried about falling off a bike, one thing, and the consequences of that, for example, would be a concussion. So you go to the hospital. So what the protection that you buy in that case is essentially a bike helmet. And that's essentially an insurance policy. You're kind of investing some money to lower risk. Now let's assume for the second that we actually wear the helmet. And second, there's all these arguments about whether or not, helmets actually protect, people from bike accidents, and forget about all that, because the truth is that it probably doesn't really protect you if you get run over by a car. But if you just simply fall over and hit your head, it actually is a big buy down in sort of the risk level. Car accidents are another one, right? We buy car insurance. In fact, we have to buy car insurance. And there's really good statistics on how risky it is to drive a car because there's been a lot of car accidents. So insurance companies take all of that actuarial data and they boil it down to profiles of risk based, and then they assign people insurance rates based on where they fit on that profile. So the consequences, injury, death, getting sued, again, your protection mechanism here is to buy insurance. Now your risk of having the accident isn't actually lower necessarily, but presumably you drive better because you're carrying insurance. A lot of people think that if you carry insurance, you can actually drive kind of more recklessly, but of course that's silly. So insurance rates are based on statistical distributions of this huge data set. And so the uncertainty in those estimates is actually pretty low from a statistical standpoint. So in the flood world, things are significantly more complicated. We know that the hazards are from flooding, hazards from flooding, storm surge, excuse me, the hazard is flooding from storm surge. The consequences are property loss, life loss, those kind of things. Protection, you buy flood insurance, or in the home mortgage case that's backed by the federal government, you're forced to buy it. And presumably then, your sort of your tolerance for some event happening is actually increased, or your risk is lowered. So rate zones are the way that FEMA indicates this. And on the right is a rate map from somewhere in the Northeast, I forget. There's a bunch of lines on it, but the essential point is that the purple, excuse me, the bluish speckled area is the zone in which someone has calculated that there's a 1% annual chance flooding event that could occur in that stippled area. And actually, if you squint here, there's actually elevations on it, water level elevations, meaning that there's a 1% chance in one of these areas that the water level is going to get to, let's say, 9 or 10 feet. So this is what the rate map kind of looks like. What happens is that let's take one of these lines and pretend there's some very big houses on it, and some of those houses are transected by or intersected by one of the lines on this map. So the FEMA says, well, you're either in or you're out, right? And so that's really called a deterministic kind of binary situation. You either pay insurance if you're inside this zone, and you don't have to if you're outside of this zone. One of the things that's definitely true, though, is if you live near a zone, you should buy insurance, because again, there's uncertainty in all these lines, and it's almost certainly not true that being on one side of the line versus the other is in fact an actual realization of the risk level. So again, we're going to come back to how FEMA might be addressing this in the near future with some more sophisticated statistical techniques. But the bottom line is that right now you're either in or you're out. And again, I can't see the chat window if anyone's asking questions. So Anna, just kind of verbally interrupt me if you need to.
Not yet. They're just absorbing it all.
Okay, and I am going fast. I'm sorry, but I get excited about this. So again, these rate maps are based on available data, right? Just like the auto insurance, rate determination. The problem is that the data on tropical cyclones is really sparse. It's sparse both in space and time. So even though we've got 100 years of car accidents, in every single year, we've got hundreds of thousands of events. But in the hurricane world, over nominally 100 years or so, we've got roughly 700 to 1,000 events, which again, if it was all in one place, that'd actually be a lot of data, but it's not. As this picture of hurricane history shows, it's all over the place. So in this particular event map, there's, I think, 1,200 storms over that 150-year period. And the intensities of the hurricanes, the speeds with which they're transiting, through the atmosphere, they're not equally well resolved statistically all along the US coast. So this is really the data challenge. Well, how do you deal with this? And a consequence of this sort of data sparsity is that the uncertainty estimation in the underlying distributions that describe the hurricanes and their effects is actually very, very high. So one example of this, let's go back to the rate map. So again, in this particular, my rendering of this, there's this special flood hazard area, which is basically anywhere where there's some appreciable risk according to FEMA. And again, that's within the 1% flood zone. So these properties that are not in the zone, this is again, Mexico Beach, Florida, right before Hurricane Michael made landfall, which was, I think, the biggest, the most intense storm to ever make landfall. I mean, it was massive. So here you go, right there. There's a bunch of properties in here, and if they're sort of hanging their hat on the fact that they're outside of this flood zone, meaning that land that they're on is actually higher than the expected flood level, then they should be fine, right? Well, not so much. So that entire area was totally destroyed. I mean, it's actually leveled. So the question is, well, what's wrong? Is it the map? Is it the data? Is it the model? We haven't even defined model yet. Or is it the statistical methods or the mapping methods, the process of going from statistics and data to drawing the map? I mean, what went wrong? Well, I mean, it turns out that for instance, in this case, clearly not in the zone, but clearly at risk. and this is the problem right here. So how, these maps are, they're people's best estimates of what the risk profile or the risk situation looks like. But in many, many places, they substantially underrepresent the actual risk levels. And this is just one example from sort of recent history. If you look up in the Northeast during Hurricane Sandy, you can find, dozens of examples of this kind of thing. Okay, so that's kind of the staging of the problem, if you will. So what we need are detailed hazard risk delineations to make better decision making, to make better and more informed decision making across a wide variety of spectrum and time, from prediction and forecasting. So not only from the statistical standpoint, but just here comes a hurricane, right? Where's it going to go, and what in particular are the storm surge levels likely to be, or the wave levels likely to be. So we've got short-term, we've got long-term, predictions, sort of climate-like predictions into the future. Emerging issues significantly complicate this, like climate change impacts, compound flooding, which is the co-occurrence of both coastal storm surge and riverine flooding coming downhill and meeting in the coastal zone, and then significantly interacting, such that the integrated effect of both of those is actually worse than just both of them separately and then kind of lumped together. That's a very active area of research. I mean, there's not a lot of great modeling tools to handle that kind of problem. So this sequence here of pictures really just says, we're talking about a variety of scales overall when you think about hurricane risk. I mean, we need global models to set large scale atmospheric patterns that steer things like hurricanes. That information somehow has to get downscaled to sort of the level of the hurricane in the upper right picture. Eventually, we got to compute storm surge and wave heights from that, so that we can do things like draw some maps that again convey what the risk level or the risk profiles actually look like. So again, on these rate maps, we need to predict long-term hazards and short-term events. Insurance rates are basically 30-year mortgage kind of timescales. The problem with these rate maps is that they're really not intended for designing and planning. They're really meant for insurance. And so in many cases, however, it's really the only source of information that not only people, but groups like planning groups or conservation groups or whatever the case. It's really one of the only tools that they have to say, well, give us an estimate, give us an idea of what the risk levels from hurricane-driven storm surge actually look like. One of the things about these maps is if you look at them, and maybe y'all have done this in class or for some other related activity, but there's AE zones, and then if you look around, there are VE zones over here. And so the difference between those is that VE zones also have a fairly high amount of wave height. So storm surge, which again I'll describe better in just a second, storm surge is a wave, but it's not really the same type of wave, at least in some sense, that you see wind waves at the beach. So the waves that are crashing at the beach in storm surge, they're both waves, but they're operating sort of in different spatial and temporal scales. Nonetheless, it's still a wave. So in these VE zones, there's the expectation that there's going to be a lot of storm surge, but there's also going to be some component of, let's say, the total water level, or really the damage that's going to get done, is going to be attributable to wind waves themselves. So that's kind of one of the distinctions on these maps. And so in order to tease this apart and make a map that has both of these on it, you got to have models which actually can do both the storm surge and the wave problem. And those are not always the same models. Anna mentioned earlier on that we run a model called ADCIRC/SWAN. So ADCIRC actually is the storm surge part, and /SWAN is the wave part. And that's an integrated piece of software at this point that actually does allow us to get to sort of that level of distinction. Having said that, once we compute all of our data, somebody else's job is then to draw the maps. And so we don't compute the maps, we compute the data that goes into the maps. So again, I'll circle back to that. So the primary coastal hazards are basically winds from storms, tropical hurricanes, and extratropical, although we're not going to talk about extratropical here. And then the storm surge and the waves that results from that. So this is actually a cartoon. I meant to credit this. This is from Climate Central. So if you look at a big chunk of the coast, you've got high winds offshore that are blowing on land and tearing shingles off of roofs, and sort of at the coastline and some distance within that, there's the storm surge. The storm surge propagates upland to some level. And then again, back to the compound flooding comment, you also, if the timing is right or the storm is slow, there's a bunch of other parameters that are critical. But if you've got a bunch of precipitation being dumped on land and it runs downhill and meets the storm surge, then that's actually a fairly big problem that has to be addressed. FEMA, by the way, doesn't have a way of addressing that right now. In fact, NOAA, whose job it is to do things like predict storm surge, doesn't have a very good way of doing that either. But they've funded several groups, including us, to actually look at some techniques for dealing with that problem. Just a comment on coastal storms. I said extratropical, we're not going to consider them in this talk. They're actually relatively frequent. The East Coast from basically Georgia on up through the Gulf of Maine, up into the Bay of Fundy area, gets 3 to 6 big ones a year. And those are actually more important along the Northeast coast, say from Chesapeake Bay, up north. They're less important south of Cape Hatteras in terms of what drives the sort of the underlying risk. Tropicals really drive the risk at basically the 100-year level south of Cape Hatteras, all the way into the Gulf of Mexico. And at least in the North Carolina coast, they're comparatively infrequent at about 0.3 per year, or one one important hurricane event every 3 years. That's roughly the frequency that they occur on. So again, just to say that there's a bunch of there's two classes of storms, and we're kind of going to throw out the extratropicals. So what causes storm surge? Well, I mean, fundamentally, wind is pushing the water somehow. And this is a little schematic from the COMET program, which has got a lot of really good graphics in it. So a hurricane has a low pressure minimum sort of in the center of the storm, and that low pressure signature actually picks water up. And if you're way, way, way offshore where there is no land, then that's really the storm surge is really almost entirely due to the surface pressure differences that pick the water surface up. And that's kind of nominally what this larger, moving my mouse, realizing that you may not be able to see it, but there's sort of a larger hump here of water, and that's really picked up by the pressure differences. But as you get closer to land, what happens is the winds are pushing water, and that water hits the land, and just due to sheer mass conservation, if the depths is getting shallower, then the water height's got to get taller, and that's really kind of one of the more basic ways of thinking about what it means for winds to drive water and have that turn into storm surge. Another quick look at that is that this is, I think, Hurricane Fran, actually. I can't remember, doesn't matter. Coastal North Carolina, if the storm, the winds on a hurricane rotate essentially counterclockwise, which means that if the storm is moving to the due north in this case, the winds that are on the right side of the hurricane are actually a little bit stronger than the winds on the south side. And that's just due to the translation speed of the storm itself. So that storm moving forward with winds blowing on the right-hand side in the same direction, means that the winds are a little bit stronger there. So the winds on the right side are piling water up on the coast. The winds on the other side, the opposite side, are actually pushing water off the coast. So if you're careful about the way you model this or look at the data, you can see that there's a difference in sea level sort of along the coast here due to the orientation of the winds as they're blowing on or offshore. Not so important for our discussions, but maybe, interesting fact. Here's another one. So if you take the equations of motion and you boil them down and you just look at some really basic balances about what's going on, it turns out that the water level is due to a couple of things. If the wind speed, which is this tau term, if the winds get higher, the storm surge gets higher. That's obvious. If the depth of the water gets smaller, so that this term in the denominator gets smaller, then the storm surge goes up. So in other words, the shallower the water, the larger the storm surge. And that's the mass conservation issue that I mentioned a second ago. What's not so obvious is this W. And W is a parameter that says how wide is it from the coastline out to some part of the ocean. And that part of the ocean is called the Continental Shelf. And if you've heard of it, great. If not, if you look at this map over here and you were to draw a distinction here along where my mouse is running, or whether the light blue near the coast sort of turns darker blue as it goes offshore, that's about the place where the water depth starts to change really abruptly. And that's at about roughly the 100-meter depth. So in other words, in 300 and something feet of water, that point up to the coast is what we think of as the continental shelf. Where that continental shelf is wide, the storm surge is bigger. And the reason for that is not entirely clear. It's not easy to describe quickly. But if you look at places where the continental shelf is wide, for instance, this area of the Texas-Louisiana coast, this area of the western Florida coast, northwestern Florida coast, all along the U.S. East Coast, and in particular up from Chesapeake Bay up into the Narragansett or Cape Cod area, those are wide continental shelves. So if all other parameters are the same, meaning the hurricane strength and winds and all of that, places with wider continental shelves will have larger storm surge. And so, for instance, if you look at the east coast of Florida, you can see that this change in depth here actually gets closer and closer to the shore. As a consequence, the same storm will not generate very much storm surge along the east coast of Florida. So anyway, that's just a little bit about the dynamics of what's going on. There's a bunch of other factors that matter, including the way that buildings interact with the wind field near the coast. Think of New York City or some other big metropolitan area. The type of vegetation that covers the land near that, whether, because that changes the frictional environment the winds are blowing over, and all of that is important. I think I gave a reference or a PDF of this Rezio and Westering article review from Physics Today. It's a really good article, and it sort of gets into some of the higher level details, if you will, about these kind of issues. So in order to simulate any of this, whether or not it's the hurricane or the storm surge, you got to have a model. And models it's kind of a loaded word. It means a lot of different things to a lot of different people. But the bottom line is that a model is used to help predict something. And it says about the future here, but it actually can help you interpret or predict the past, right? In other words, if you have a model, you actually need to do a lot of simulation of historical events to make sure that the model is computing answers that make sense to the observations that occurred historically. So think of, from computer model to conceptual model. So a computer model like a climate model, which are enormously complicated pieces of software. That's a model. Somebody sat down, a group sat down, and they wrote out the equations, and they came up with the software implementation of that that physical system that is the thing that is used to predict the weather or the climate in this case. The FEMA map, the rate map, is a model, right? It's basically saying, well, maybe I don't have all the information in the world that I need to assess what the flood levels are at this particular location, but the map can help with that, right? It can say, assuming all the data going in is as best as it can be, and we already saw an example where that wasn't true, but let's assume that it is, then that's still a model of it's a prediction about the future. Basically, you're saying, if I live here, what is the probability that there's a flood level reaching some height, and by the way, how much insurance premium do I have to figure out how to pay? And then a model of an architectural or an engineering rendering is a model, right? It's somebody's idea about the future, the future of a project, for example. So these are all models, right? And there's a little statistic up here that y'all may have heard of. All models are wrong, but some are useful. And this is George Bach said, it's kind of a famous quote, but he didn't say this in the context of computer models that are solving physics equations. He really was talking about statistical models. Let's just, linear regression, for example. But it's always good to keep this in mind, because it is true that no model is perfect. All models have errors, data have errors, and all of those errors propagate into the solution or the answer that you're trying to get. And you have to be aware of that before you say my model's the best, or whatever the case may be. Another example where we're thinking about looking into the future is sea level rise, for example. I mean, we really can't do anything without a model in this case, because this is a very long range projection. And for instance, this is the coast of North Carolina in this perspective view, and this is the ADCIRC model in North Carolina. And this is just really to say that the geometry here is really, really important. It's very complicated. A lot of bays, estuaries, little fingers of rivers going here and there. And all of that's really important to get right if you're talking about how much water is going to be here during a certain hurricane. The problem, of course, is that if you look at the coast of North Carolina in this upper right, these are places where NOAA has tide gauges. There's, I can't count, 6 of them in North Carolina. There's actually another one down here, but for some reason, it's only intermittently available. The point is that it's not very much. And what we really want to be able to do is say something about risk levels in between where there's observations. And so that's another thing that models are used for, basically interpolating between places where we do have information. So we'll use these observations at these star locations to make sure the model is doing what it should be doing. And then we can have some level of confidence that in between those locations, we can attach some level of uncertainty to those predictions in between the observations, and that helps us sort of move forward. and if you think about sea level rise, I mean, here's a couple of the projections from, this is not the most recent climate assessment, but it's probably the previous one. There's 5 different projections on here. And in the year 2060, which is, by now only 40 something years away or 40 years away, there's a lot of uncertainty in where sea level is going to be. This data used to create these or to generate these curves are all based on observations. That there's no dynamic model running around computing that. Now, what we do is take this information and shove it back into the storm surge model to say, well, what happens if we have the same type of hurricanes coming in and we have 1.5 feet extra of sea level, right? That's a critical question. So we try to address that sort of formally, both from a physics standpoint as well as from a statistical standpoint, to help say, well, if that rate map that we have right now is the best it can be for this year right now, well, what about 30 years from now? That's a question that we have to address a lot. I talked about the sparsity of the models, sparsity of the data. So again, back to this, there's 150 years of observed hurricanes. Of course, hurricanes have been occurring for a lot longer than that. But only in the last 50 or so years are all the parameters that we really need fairly well observed. So 50 years is not a lot of time when you've got, think about North Carolina, 1 in 3 hurricanes per year. So that's 14 or 15 storms over a 50-year period. So here's what that looks like spatially. So here's all the hurricanes that have occurred. If we want to say, well, let's just look at a particular part of the coast. I said North Carolina, but this is actually for the Northeast region. It doesn't really matter for this point. And say, okay, so there's all the storms in that red box that go through that red box, right? And so here's what it looks like when you zoom in. That's not a lot of data. They're important events. It's important to understand them, but think about the car example where if you're a person who's aged 35 to 45, you live in, Texas or Maine or whatever, there's a lot of data available to slice that risk profile down to that particular person. So the analog here is, well, at any given point, right, along this, just pick, part of this part of Long Island Sound or whatever it is there enough data there? Absolutely not. So we have to get in between, get in between these observations, both in space and time. In the interest of time, I'm going to skip a little bit here about FEMA because, not all that important right now.
Well, and in the meantime, Brian, I do have a question in the chat.
Sure.
And where did it go? Oh, Kels Peterson, are those lines tracking the center of the storm or some sort of average?
No, it is the former. These are the actual latitude, longitude positions of the 500 and something storms that have occurred between I forget what I picked, 1950 and 2020 or whatever it is. So these are the actual paths that the hurricanes took. And associated along these paths are the associated along track parameters, like how deep the pressure difference is, how strong the winds are, how far away from the central part of that, from the center point, is that strongest wind. So all of that is included in the data set. I'm simply just showing each track as an individual color here to give an idea of the density. I mean, again, from the standpoint of this upper plot here, it looks dense, but it's not, given the time range that is important. So I think that answers that question. But one way to think about the data sparsity problem here is, if we're interested in predicting, hurricane impacts over, let's say, a 1% chance level, so over 100 years, right? Well, we would need 100 years of data, and we would ideally like to have one event per year would be great. And we'd like to have that everywhere along the US coast, right? So that the sum of those 3 problems or 3 constraints means you got to have a lot of events in your data set. And this just simply doesn't qualify from that standpoint alone. So if that doesn't answer the question, please let me know, and we'll make sure we can come back to it. So when FEMA computes a rate map or says we need to compute a rate map, I mean, FEMA doesn't do it, right? They hire contractors to do it. The process is kind of as follows. It takes about 8 to 10 years to go from conceptualizing that we need to compute some rate maps when they say we got to update the rate maps, and this happened after Katrina, right? Katrina in 2005 sort of opened people's eyes about how inadequate the current maps actually were. So that motivated a whole lot of desire to recompute them. And it also, as a consequence, said, where's the money going to come from? Because it is not cheap to do this. Once that was all figured out, the process, is basically like this. Well, let's do some modeling to come up with statistics. There's actually kind of two parts to the model. There's the storm surge part, which is this leftmost box. There's another part here which I don't know much about, and in fact, it's actually probably one of the most non-rigorous parts of the whole process, which is once you have storms and waves at the coast, how do you get that information up onto land? And that's actually what this WAFIS program does. And then once you have all that sorted out, then you can draw the maps. Okay, and that's largely all a technical process. And then the maps go to the communities, like pick a county in North Carolina. FEMA says through the state of North Carolina, here's a new set of maps. We want you to show them to the communities and get them prepared for whatever changes are implied in these rate maps. And then those maps have the opportunity, the communities have the opportunity to appeal those maps. And that part is can be very long and in some cases may exceed 10 years from the inception of the project. But these are entirely political and economic issues that don't really have much to do with the physical models of how you deal with storm surge. So I'm going to need to skip here just a little bit because I'm kind of running long. But here's how we actually turn this picture on the left is the same, just a different version of the same picture I showed a minute ago of all the hurricanes that have occurred. And I said, well, it looks like it's got a lot of data, but in fact, it's actually very sparse. So there are statistical methods. Joint probability approach is one of them, where you can take the data that you do have and you can inflate it in a way that goes from very sparse coverage in an area. For instance, let's look at North Carolina down here, where again, there's been basically 14 storms over the last 50 years. You can statistically represent a much denser population through this joint probability approach. And in this case, we've turned 14 storms into roughly 500 storms. And then we take each of those storms and we compute the storm surge. So that's just a little bit of an illustration. There's obviously a ton of stuff that goes on behind the scenes here, but that's kind of conceptually what's going to go on. Let me skip this one and go to this one. So I said something about model development. So now, if you want to compute the atmosphere or the storm surge, this is kind of what has to happen. These are all physical systems, physical meaning physics, and they're all constrained by Newton's laws, right? So they all start one way or the other from force equals mass times acceleration. So you take all these forces like atmospheric winds, pressures, the Earth, the moon and the sun attraction, for the water body problem, meaning tides, and you formulate this whole set of basically you reduce this to partial differential equations, okay, just complicated math equations, and then you turn these into algebraic equations, right? This is if you've heard of linear algebra, for example. Computers don't know what to do with partial differential equations, but they do know what to do with linear algebraic equations. So you can turn PDEs, partial differential equations, into these big matrix problems, which are just linear algebra at that point. And that's what ADCIRC is. So if you hear somebody talk about the ADCIRC storm surge model or the federal weather model or the federal wave model, what they're talking about is a piece of software that solves some sort of linear algebra problem one way or the other. And then if you're going to do this at large scale, for the weather or the climate, you have to have a very, very big computer to do it on. So that's kind of the overall process. And you may have heard of a model called SLOSH before. So there are kind of two main models for storm surge forecasting. SLOSH is NOAA's model. It has its pluses and minuses. And then there's the ADCIRC model, which we use extensively. It was developed at UNC and Notre Dame over the last maybe 20 years, and it's very powerful. It's got a lot of cool, sophisticated stuff in it. But when you want to use it for a problem like a FEMA problem, the computational cost is pretty high. And the reason for that is that The black squares in this right picture are where NOAA solves the problem, meaning NOAA's slosh model. And for the ADCIRC solution to the same kind of problem, we computed on these very small triangles. And this is actually not even as small as the triangles can get. So the point here is that one model is solving the problem at a fairly big coarse resolution. And it's actually very difficult to say with any confidence what's going on in between these, the vertices on this, or the intersections of these black lines. So ADCIRC's approach is that, well, that's really important detail, and therefore we're just going to model it directly. So that's really the fundamental difference here. So NOAA's slosh model, and I'm not going to get into, the statistics of the slosh model and whether or not it's, better or worse. The point is that there are different tools for different problems. FEMA used to allow people to use the slosh model for their flood insurance calculations, but not anymore. After Katrina, it was realized that you just can't do that. It's just simply not resolved or detailed enough. All models need data one way or the other. Again, back to this, force equals mass times acceleration. What we're really interested in is the acceleration of the system, acceleration of the water, of the winds. And in order to do that, we got to know all the forces. And those are the key inputs to all of these problems. I'm going to have to slide here pretty quick. I'm going to skip that. I'm going to skip that. Here's what the simulations look like for the coast of North Carolina for our storm surge problem that we computed for FEMA. The red lines in these, the red asterisk lines in this map, on these maps, are the paths of the hurricanes. And those hurricanes have, wind speeds and pressures and all that associated with them. So the colored surface is how high did the water get based on these two storms. And so what it says is that in the left-hand side, this storm generated 4.4 meters of water right wherever that arrow is pointing, somewhere around Morehead City or Emerald Isle, something like that. This other storm generated 7.1 meters. So that's 22.5 or 23 feet of water. That's big. Okay, now the differences are, there's two differences here. One is that this storm actually was more intense, right? It was simply a stronger storm. The other thing has to do with how wide the continental shelf is. Again, wider continental shelves have larger storm surge, all other things being equal. And the angle at which this storm actually approaches the coast. So each of these storms, has different characteristics, and the responses are actually quite different. And it depends, again, on these details like the geometry of the coast, vegetation cover and all of that. So we take all of these different simulations and we can turn them into these statistical 1% water levels statistically. And so here's what it actually looks like for the coast of North Carolina. This is Wilmington is, somewhere around in here. This is the Wrightsville Beach area. So for all of those, hundreds of storms that we ran and then we computed the 1% water level, it says that along the coast of North Carolina, at least in this area, these are in feet, not meters, that the 1% annual exceedance water level is on the order of 12 to 13 feet. And that's actually, if you look at Hurricane Fran in this area caused about a 13-foot storm surge, which at least from that perspective would say that Fran is about a 100-year event, 1 in a 100-year event, or a 1% chance event. So that's kind of good. And if you look at the overall coast, look at the coast overall, here's that same area, 12 or so, 13 feet of water level at the 1% chance level. But if you go north, up into the, into the Outer Banks areas, notice that the storm surge is actually 1% is actually a lot lower. And that's because the continental shelf there is actually much narrower. So there's a physical explanation for why these kind of features are. Where there's wide shelves, we expect the storm surge response to be larger based purely on that. And it, of course, it's comforting to see that shows up in the physical models because if it didn't, something would be wrong, right? So we missed something somewhere. I'm not going to talk about that. I guess I don't really have time to talk about. Well, so let me just mention this. Here's one of the previous versions of maps in the Morehead City area, and there again you'll get these slides. You can study them all you want, and we can talk about them later. The bottom line is that it is a rendering of that flood insurance rate map. And if you toggle between these two, so here's the one that was current. In other words, this was the previous version, right? And here's the new version. And it was very hard to make these kind of exactly identical in terms of the graphics, except for the differences in the water level. So you'll have to sort of take it on faith at the moment that what's really interesting here is that you look in certain areas in this red box, for example, go back and forth. There's some pretty big changes in this. Now, what's really happening is that we've just got this older map is probably 15 to 20, maybe in some cases 25 years old. And over the course of the last 25 years, we've got better data, we've got better models. In particular, we have better models for what the land surface actually looks like. So all of these things come into play, and in this new preliminary map, which by this calendar time, meaning January of 2021, this may actually be the official new map now. I actually don't know the answer to that. But one way or the other, what it means is that if you study the differences between these two maps, there are some big changes, and people have to be prepared for that. Because some people's rates are going to go up and they're going to be upset. And some people's rates are going to go down and they're going to be upset, because their question is going to be, well, if it's down now, why was it high 20 years ago? And these kind of policy and political arguments happen all the time, and they're important, right? But I don't have a whole lot to say as to, I think they're kind of silly, and basically people don't understand the underlying statistical problem, and it's really not that there's an expectation that they should, because it's complicated. But the truth of the matter is that these maps are pretty well calculated, and I think that the community, it's a big marketing job to get the community to buy into some of these changes, and I'm glad I'm not part of it. So I said this is the last part. Go back to this thing about being in or out, right? So in or out means you're on one side of the line or you're not. But the true risk profile across an area is actually a spectrum, right? It goes from zero risk, if you live in Asheville from storm surge, or even Raleigh for that matter, to some much larger value at the coast. And it's not a linear transition, but it's definitely not binary. So what FEMA is really trying to get to is this thing they're calling risk rating 2.0. Where instead of being a very hard line in the dirt or the sand, as it were, it's actually a graded risk. So in other words, if you live high up on this hill right here, you should pay less in insurance than the people that are living sort of downhill from you. That kind of only makes sense. That's how car insurance works. That's how sort of health insurance works. And FEMA's trying to get to this point because it will actually significantly rationalize the flood insurance system, and actually hopefully get people to buy into it more. And as a consequence, the flood insurance, national flood insurance program can be a little bit more self-sustaining. There's some resources here at the end that y'all can look at. This is actually, I think, I can't remember if I sent Flather or not. This is a really good article, just an overview article. This catastrophe economics, the National Flood Insurance Program, is a fascinating article. It's old now. It's 15 or 10 years old. Redesigning flood insurance is also a really good article. So with that, I know I went a little bit over, but can't help it. That's it.
And that is a very naughty picture.
Yeah.
That
actually couldn't happen.
Guys, don't use this in anything you write or a post or anything like that. It's just like, talk about fake news.
Yes. All right, so that's it. That's all I've got.
Thank you, Brian. That was really terrific. I know that we had several questions that were submitted in advance about plain language and how do you help, for example, planners, because the models are so complex. I think presentations like yours go a long way to helping with that, along with establishing that the maps that are drawn Well, somebody's going to have to use those for those hard policy decisions and those political decisions, and then all the modeling and formulas and math in the world that stand behind them are used as evidence, but we haven't even touched the political and issues, not to mention. So Brian, just so you know, an ongoing theme throughout this semester has been issues of equity and parity and those kinds of issues, and we can really see it along the coast. Now, you're just doing science, but it has to be interpreted and used for decision making. And that's where the issues. Do you have anything to say to that?
Yeah, I do. I mean, this is the more important end of the problem, right? I mean, because people can ignore the statistics. I mean, we do it all the time, right? I mean, I mean, a lot of what's happened in the last a couple of 3 or 4 or 5 years is like distrusting science and all of this. And look, what my opinion about that is whatever, except for the fact that it fundamentally affects how policy gets implemented and managed. So so it's a very hard job to sell this type of science to communities and people that in many cases don't want to know the answer, right? I mean, coastal North Carolina is a perfect example because the economy in Eastern North Carolina is not driven by the military. It's not driven by industry. It's driven by tourism. So the last thing people want to hear about is increasing insurance rates or barrier islands getting blown away, because that's the livelihood, right? And they depend on that. So, I mean, I'm not insensitive to that at all. But the truth of the matter is that over the next 20 to 30 years, right, even if hurricane occurrence rates actually stayed the same, if sea level rise goes up by a foot, then that means that those 1% levels go up by roughly a foot, and that propagates inland, and that impacts people. So if state and local agents or governments are unwilling to tackle that problem, they're only forcing it down on people 20, 30 years down the road. It's going to occur. So I don't know what the solution to that communication problem is, because people on both sides have to be willing to accept the consequences, right, of the hazard changing one way or the other, because that fundamentally changes the level of risk that people are going to be living under. And the truth of the matter is people can ignore the statistics or just say that, well, I mean, I just make decisions. Even if you make decisions and you're unaware of any of the real underlying issues, you're still doing a risk calculation, right? It's internal. But if you say, I'm going to live at the coast and I don't care, you're saying that the biggest possible event would not change your life. And maybe that's true. But at a community level, if you have a lot of that sort of decision making going on, then what happens is that somebody has to back that insurance pool. And that's unlikely to be the people that just got wiped out. It's likely to be their neighbors and their community neighbors, and the people in Omaha, right? So we as a nation have to become a little bit more risk aware in order to justify and argue persuasively that one community in the center of the country should subsidize the rates for coastal flood insurance. Well, guess what? I mean, if there's crop insurance, right, and I mean, guess who subsidizes that? The people at the coast, right? So there's a whole bunch of arguments that can be made to help people better appreciate how to deal with this.